My name is Miha. I'm a physics student from Ljubljana in Slovenia. I should first say that I'm not yet a PhD student. This work will be a part of my master's thesis. So I would like to thank my advisor, Professor Slobodan Žumar, and Miha Ravnik for help with this work. And I would like to thank the organizers for organizing the school and inviting me here. First, as I said, I will talk about modeling propagation of light through waveguide from liquid crystals with a Radial-Director profile. I will first tell you a little about why we should do it, then describe my numerical method, and finally present a bit of results. Note that these results are still very preliminary. So, guiding light is something very important in modern communications. All of you with fast internet at home probably know this. And liquid crystals have unique optical properties such as birefringence and response to external stimuli. So they are very useful for such tasks. Fibers from synaptic materials were generated pretty recently in laboratories, such as seen on these pictures. But Professor Mušević's group in Ljubljana also synthesizes longer ones and showed that such fibers can be used as waveguides as they guide laser light through them. And finally, defects in liquid crystals and defects in optical fields, as we saw in this school already, are usually connected with each other, and we wanted to explore this connection in this case. First, you probably know the four main Maxwell equations. And in our case, we can probably neglect some of the terms. For example, there are no charges inside or electrical currents. So these equations simplify a little, but still they are very friendly for computer simulations, because if you only use the second two equations, the first two ones will be automatically true. So you only need two equations, and both of them have direct time derivatives, which are the time derivative of one field is always proportional or related to only the space derivative of the other. So you can basically alternate between calculating one and the other. And because one field, the time derivative of one field only depends on the other, you don't need any information about its neighbors. They are very suitable for parallel computation, which appears to be popular these days. As I said, we can simplify the Maxwell equations if you use the relation between D and E and E and H and B. We get the above two equations where epsilon is an anisotropic tensor. From those two equations, we can directly calculate the time evolution of electromagnetic fields. But as I said, we separately calculate E and H, so they are known at different times, but we can also optimize the method if they are known at different places. So we use a so-called staggered grid. An example is shown here on the right bottom. Because in liquid crystals, the Q tensor and so also the dielectric tensor is both anisotropic and non-uniform, so we cannot choose a coordinate system where it would be diagonal. We had to take this into consideration when implementing the methods. So this method is pretty general. Before using it to calculate any unknown new phenomenon, we tested the method with basically three well-known examples. The first one, a uniform director profile. You probably saw this one several times in the school. Basically, we calculated how much of the light comes through if you put between two cross polarizers a thin film or a sample of a nematic liquid crystal where the nematic formed an angle with the first polarizer, for example, and you see a sine square dependency. It matches very well with the theoretical prediction. Additionally, we explored a simple case of refraction on a straight interface very near the Brewster angle, so you can see a little of the light reflects back, but most of it refracts through. And finally, we also calculated a simple case of a periodic structure, basically just two layers of different dielectric constants alternating. And again, the method predicted correct positions and width of the photonic band gap. In this work, we focused mainly on a radial-director waveguide. The schematic is shown on the picture above. Basically, in the center of a cylinder, there is a singular +1 disclination line, and all around the director is radial. I said that they were generated using schematics, so there should be layers visible, but those layers are very thin compared to the wavelength of light, so they can be neglected, and we can calculate as if this was a nematic. Although in a nematic case, we don't get a disclination line because the director escapes into third dimension. We simulated fibers with a radius of around 10 micrometers, and what we did was shine a very short laser pulse inside and just see what happens. To simulate very long waveguides, we use periodic boundary conditions at the end, so the light could go several times through a computation cell. These are pretty much the first results. It's a direct snapshot of the electric field inside the waveguide. The first thing we can see already on the first part of the picture is a small hole, a dark spot near the center, because there is a topological defect in the liquid crystal of the disclination line, and pretty soon topological defects also forms in the optical field, which means there can be no light there. Pretty soon, because of the difference in observed refractive index, light on one side observes the ordinary and the other the extraordinary index. You can see the beam distorting a little, but after a long time, the beam really loses its shape, at least if you visualize the electric field directly. A somewhat more illustrative visualization is this one. There are basically intensity regions, so what's plotted here are surfaces where the light energy density or light amplitude is at least 5% of the maximum or something like that. And you can see at first the pulse is roughly spherical, but already a dark spot at the center is visible pretty soon. And then the pulse distorts a little and splits into 8 parts. Those 8 parts, or 8 intensity regions, appear to be a relatively stable configuration. They distort a little and change shape, but their positions are very stable. They are positioned in 2 ranks, which correspond to 2 propagation modes, or 2 eigenmodes of the waveguide, and they are positioned diagonally to the polarization of the incident light, which in this case was in x direction. I also took cross-section of both of these propagation modes, so we can see their polarizations. If you look carefully, it's probably more visible in the second case than in the first. In both cases, the polarization, if we use it as a director, forms a -1 disclination line, such as the one shown here. So a +1 disclination line in the director field causes a -1 disclination line to form in the light. As I showed before, you can see that those ranks appear at the same positions, those intensity regions. The same happens here, except that the disclination line is rotated by 45 degrees with respect to each other. So in one case, the high intensity regions observed are polarized radially, so they observe the extraordinary refractive index. And in the second case, they are polarized tangentially, at least in the high intensity region, where they observe the ordinary refractive index. So these are pretty much all the results. To summarize, we implemented a simulation method to model the propagation of light through media with pretty complex dielectric tensor. It can be non-uniform, fully anisotropic, so non-diagonal, and it can also support currents or conductivity of the material and such things. It uses direct solving codiscretized Maxwell equations, as I've shown above. It can also be very fast because it can be parallelized, run on a large number of computers and that. In the results for this case, we show that a topological defect in the liquid crystal waveguide causes a topological defect in the optical field. One defect is +1 disclination, the second is -1. We also studied the propagation modes of these waveguides, and we showed, I showed them above, and we predicted the splitting of a single laser pulse into 8 different intensity regions. And that's pretty much all. Thank you.